Hello everyone, let's discuss the seismic load application in Midas Gen. The seismic load application will include the static earthquake forces, response spectrum loading onto the structure as well as the pushover analysis of this particular structure. The focus will be on the procedure rather than the outcome. So to understand the procedure of working with the software, we are going to start with the static seismic loading. To apply static seismic load, we go to load, static loads. And before we apply the seismic load, I have to convert the loads to masses. As per the code, we have to consider 100% of dead load, 25% of live load for storage structures. This is not a storage, so I'll press OK. Now to make sure that the cell fit has been converted into mass, I'll click on convert cell fit into mass in the structure type. So once it's done, I'll apply the seismic load. Add. Okay, I need to add the load cases as well. So let me add earthquake major, earthquake, and let me add earthquake orthogonal. So I've added the major and orthogonal load cases in here. Let me apply under earthquake major. I do not know the major and orthogonal direction right now, so I'll be assuming that x direction is major, y direction is orthogonal. Later on when we get the angle, I'll revise this. SC zone 4 source type B 10 kilometers. For period, I'll use special moment frame for concrete. Ductility 8.5. Since I want to apply an x, y 0 for y, no accidental eccentricity. Apply. Earthquake force is added for x. For y, change x to 0, y to 1. So I've applied earthquake force in major and orthogonal directions, the static seismic load. Let me apply the dynamic load now. I'll define the function, design spectrum, UBC 97, same site specific definition, zone 4, source type B, 10 kilometers. Okay. Now let me add the load case for major direction. Auto search angle, checking on auto search angle, software will automatically calculate the most critical excitation angle. As per the code, we are supposed to apply earthquake in most critical direction, not in x and y. So I've checked on major, so software does the calculations for the excitation angle. Scale factor is importance factor over response modification factor. I select the function and press add. Response spectrum is added for major. Let me add for orthogonal as well. For orthogonal, I change this with ortho and press add again. Load cases, I define the two load cases. For the results of the response spectrum, we have to define the number of modes. So I'll consider Lanchos and I'll consider 30 modes to be considered for the eigenvalue analysis. So I've entered 30 in here. Using the 30 modal combination of 30 modes using the CQC combination, we'll be getting the results for the response spectrum. So let's run the analysis now. So analysis is complete. Before we check any result, let's check the vibration mode shape, making sure that we are getting more than 90% mass participation. 94 and 90.52 both are higher than 90%. That means we are getting more than 90% mass participation, so our response spectrum results are correct. We don't need to increase the modes. If the results for response spectrum are correct, that means I can check my angles now. So angle, as you can see, major direction is coming out to be 172 degree. Major direction as obtained in here is 172 degree. That means 8 degree is the critical angle, and as you can see in here, orthogonal is coming out to be 82. So the most critical direction for earthquake force application is at 172. That would be somewhere 8 degree from the negative x axis, 8 degree from negative x, somewhere in this direction. Now I'll have to revise my static earthquake forces accordingly. So let me show you basically what's happened in here. So I have got the response spectrum loading at 8 degree. So this is the angle at 8 degree. It says that the earthquake major angle is at 8 degree. So this is the major direction for earthquake force application, and the orthogonal is over here. This is orthogonal. this is y, and this one is x. So basically what I've got to do is I have to apply the earthquake forces. If you remember, the static earthquake forces were applied in global x and global y. Now that's incorrect. We have to apply in the major direction. So to apply the static earthquake force in major direction, basically I'll be entering the scale factor for negative x, and positive y. So I have to enter the scale factors. Cos 8 with a negative sign will be the scale factor for x, and sine of 8 will be the scale factor for y, resulting in earthquake force in the major direction. This is the earthquake force for major, EQ major. As I said, for x direction the scale factor would be cos of 8, cos 8, 0.99, so minus 0.99 for negative x, and the y direction factor will be sine 8. Point 139. This will result in the resultant seismic load in the major direction. Likewise, I'll have to revise my orthogonal. So sine 8 was 0.139, and as we can see in here, this is 8-degree angle. So cos 8 will be y and sine 8 will be x. So x factor for orthogonal would be 0.139 and y factor will be 0.99. Alright. Once I have entered these factors, our static earthquake forces have been corrected. Let me run the analysis. Now we have to calculate the scalar factor. To calculate the scalar factor, let's firstly check the scalar factor static seismic base shear. To check the static seismic base shear, right click properties, seismic load profile. In here the component will be SRSS. I'll go to the ground level and check the story shear. So 4029.62 static base shear 4029.62 kilonewton, that's the static base shear, would be same for x and y. Now let me calculate the dynamic base shear for major direction, and we'll need dynamic for orthogonal. Let's get the values. To check the dynamic base shear, I go to results table, story. Software provides story shear response spectrum analysis. I can select these two. Press OK. It's better checked in story shear force coefficient, and at first floor I have to check the base shear values. So these are the values for major. Let me copy. For major, these are the values in here, and I'll copy for orthogonal direction as well at the ground level. RS ortho, Control V. I have to take the SRSS, x square. Since these values that we have copied from Midas Gen are for x and y, global x and global y, I have to take the SRSS to get the resultant story shear in most critical direction. Alright, so I'll take the square root again. So basically square root of F12 and G2, F2 and G2, F1 and G1 square and this one is for F2 and G2, that is the orthogonal direction. So this is the resultant for orthogonal, and this is the resultant dynamic base shear for major direction. Now let's calculate the scalar factor. Scalar factor, since for regular structures, our structure can be considered as regular. For regular structure, scalar factor is 0.9 times static base shear over dynamic base shear. So this is the scalar factor for RS major, and for orthogonal 0.9 times static base shear over dynamic base shear. You can take a decision over whether the structure is regular or irregular structure. There is irregularity check as well. You can perform that check. If not, you can take decisions based on the ASC 41 recommendations. Anyhow, you have to decide whether the structure is to be classified as regular or irregular. The difference would be the factor. 0.9 would be changed to 1 if the structure comes out to be irregular. So I've got the scalar factors 1.13 and 1.21. These are the scalar factors. Let me go to results, load combination, concrete design. I'll auto generate. There are some combinations from previous simulation. I'll just replace those. ACI 31808, that's the code I'm going to use. Scalar factor is 1.13 for RS major. And for orthogonal 1.213. For RS orthogonal, add this. I'll consider the orthogonality effect for the major and orthogonal. So 100% in major, 30 in orthogonal, and 100 in orthogonal with 30% in major will be considered. These are the combinations. As you can see in here, the 100 and 30% rule as well as the scalar factors have been applied for major and orthogonal earthquake forces, dynamic earthquake forces. So I've got all these added in here. As you can see, the scale factors as well as the load case. Anyways, so we have correctly taken into account the major and orthogonal considerations. We have calculated the scalar factor. So we are good to run the design. Let me run the design for the purpose of getting the reinforcements. Let me remind you that design to be performed. Okay, so the design is complete for the beams and columns. Let me just update the rebar. Select all, update rebar. Update rebar will basically place the reinforcements in the column members. As you can see, column 1 and 2 have been assigned the reinforcement. Likewise, let me just update the rebar for the beam. So a single rebar has been assigned to all the beams. Update rebar was placed just to put the reinforcements in beams and columns. Likewise, I'll perform the design for shear walls and place rebars in the shear walls as well. So select all, update rebar. So once beams, columns, shear walls have got the reinforcements, these will be used for the automatic calculation of pushover hinges. I'll go to pushover and then define the global control. In here, I'll add 100% of dead load and 50% of live load. Next is the load case definition. Add. I'll define load case for X direction. P delta analysis will be considered. Initial loads will be considered for story shear as well as the displacements. We have to use the displacement control. Master node will be the node coinciding with the center of mass. So basically, if I display you the center of mass, let me just activate the roof. And let me display the story diaphragm. We have considered rigid link in here, and as you can see, the center of mass lies in here. We can check the coordinates as well. Now corresponding to this center of mass, I've got to select a node which is exactly with the same x coordinate in order to have no relative deformation between the master and slave nodes. So I'll be required to add an additional node in here. Let me check the coordinates of center of mass. Results table, story. Since I have not checked on the calculation of eccentricity ratio, the center of mass for the roof is not available in there, but can check from here as well. Story mass table for the roof. Center of mass is located at x coordinate is 29.1743, y coordinate is 10.73785. Let me change the units to feet. Okay, in the decimal places, whether it's meter or feet. So basically what I've got to do is I have to create a node at 10.3785 meters. Let me go to node element, create a node. The node will be created with x coordinate as this one, and y coordinate will be, let me copy this 29 and control C. Let me copy it in Excel, control V, 10.3785. I will enter y coordinate as 10.3785. Apply. Oh, okay. Display the nodes first. 10.3785. Apply. Where am I getting the node? If I put the mouse cursor over here, it detects the coordinates as 31.6992. Alright, so let me add over here. The y coordinate is 10.3785, so I'll enter 10.3785 in here. Likewise, I have to add a node in the y direction. So say I'll take this node as the reference for x. This node is 31.6992 and the midpoint is 27.7386. The distance of center of mass is 29.1743. So I'll change x to 29.1743. I will add a node in here. Let me check whether the elements are intersected. Yes, they are, and the nodes are connected with rigid links as well. As you can see, I have created a node exactly coinciding with the center of mass. So if I display the node number, basically node number 420 will be having the same x coordinate as center of mass. So since delta y and delta z are 0 between these two, that is center of mass and this particular node, I'll be using this for x direction translation, and I'll use 421 for y direction translation in the pushover analysis. So let me run the analysis. Let me undisplay the story diaphragm now. So I was defining the load cases. Pushover load case, add. I'll add load case for x direction. Consider P delta. Initial loads will be considered for summation. Displacement control. Master node. As I mentioned, we'll be using node number 420 for translation along x. Let me enter an upper limit of say 0.6 meters, a large value. I'll uncheck this to get the complete curve. We'll use mode shapes. Now I have to choose which mode shape to consider. For that, I'll be going to results, vibration mode shape table, and I'll check which mode. The very first mode is giving me 61% mass participation for x, and the second mode is the major mode for y. So I have to use first mode for x direction. So mode should be 1, scale factor is 1, add, apply. Node case is applied in x. Let me apply for y direction. For y direction, I'll be using the same definition except for the master node that will be changed with 421. The deformation will be dy and mode will be second mode. So second mode is to be considered for y direction, and I've got the two pushover load cases. Let me continue. So load case definition is done. Now I define the pushover hinge properties. Let me define firstly for the column. I'll use the FEMA hinges. As you can see, if you click on yield surface, you can see auto calculation of the FEMA hinge for y direction as well as the z direction. Apply. For the reference y, I am considering only the moment hinges for beams, columns or shear walls. I believe you have got the word file as well. You can refer to that description or the presentation that we have. For beam, I will just consider the major axis bending for FEMA hinging, and as you can see, this will be auto calculation as well. Since I have put the reinforcements in the beam members, software can calculate the hinge properties automatically. The last one will be for the wall. Moment hinge, FEMA type, auto calculation. As you can see, auto calculation. So I'll press OK. I've got the pushover hinges for beams, columns and walls. Let me assign these. So I'll double click on reinforcement for the beam. So all the beams which are having reinforcement, if I drag and drop the beam hinge, it will be assigned. Now let me select all the columns and drag and drop column hinge. The beams and columns have the pushover hinge now. Now for shear walls, I'll select all, select and drag and drop the wall hinge. All the pushover hinges have been assigned, and now if you want to check the properties, for example for the beam, you can click on pushover hinge property. This is the actual FEMA curve calculated based on the reinforcements and the concrete strength that we have specified, and this is the definition of the FEMA curve. As you can see, this is the yield strength of the this particular element. This is the yield strength calculated automatically, and these will be used for comparing the deformation limits, and software will automatically specify whether it's immediate occupancy, life safety or collapse prevention. The hinge properties have been assigned now, and I'm good to run the analysis. Pushover analysis is complete. Let's get the pushover curve. So this is the capacity curve I'm getting for x, and for y direction these are the capacity curves. Let's discuss firstly for the x direction. I'll click on the FEMA here, and to get the pushover curve for the exactly the same site specific definition, we used SC zone 4, source type was B and 10 kilometers. Okay, as you can see, it displays with a green curve. Let me just undisplay the red ones. The intersection point of green curve and the yellow line is the capacity curve, and the green curve is the demand. The intersection of this demand curve with the capacity gives us the performance point. Corresponding to this performance point, I am getting a target displacement of 0.195. So basically what I have to do is and the base shear that I'm getting in here is 1956. 1.956, maybe one more decimal place. So 0.195 is the target displacement. I have to increase it by 150%. So actual displacement which I have to apply will be 1.5 times this particular value, 0.195. So instead of 0.6 meter being the final displacement, I can just use 0.293. Let me check for y direction. For y direction, 0.1045 is the intersection. 0.1045. So 0.29, let me just use up to 3 decimal places. These will be the final displacements that the structure is supposed to resist under the seismic loading. Let me discuss the pushover curve again. Basically what we do in here is, this is the base shear versus displacement curve. We convert this, considering the first mode to be the considerate one, convert it into a spectral capacity spectrum, and for the demand spectrum we draw the response spectrum function. Response spectrum function is to be drawn as per the site specific requirements. So whichever definition we used in the response spectrum loading, we use it in here, and it gives us the performance point. Performance point basically signifies that for a given earthquake loading applied onto the structure is going to behave non-linearly. As you can see, this is not written as elastic, so the structure does behave non-linearly, and the performance point tells us what will be the dynamic base shear considering the non-linearity of the material, as well as what will be the maximum deformation of the structure under a given earthquake. So maximum deformation is 0.195. Note number 420 cannot deform more than this one, but since ASC 41 specifies that the structure should be displaced 1.5 times this value, so that after this value is exceeded, the structure doesn't experience sudden failure. This is why we have to multiply this with 1.5. These are the spectral acceleration and spectral displacement values, effective period. Can we check from here? Basically, if that's clear, let's revise our pushover load cases. So instead of 0.6, I have to apply for 0.293. For y direction, I have to use 0.157. Now I can run the pushover analysis for the final time. The pushover analysis is complete, as you can see now. So basically we are getting up to this point as itself, because the displacement in here would be the value that we have limited in here, 0.293. So this would be 0.293, the last point that I am getting for x, and likewise for y direction. So the benefit of capacity curve is to get the performance point. The performance point can be obtained again. As you can see, it will be unchanged as C zone 4. We have used the performance point to get the target displacement. So we have got this in here, but the structure is not supposed to be designed only for this displacement, but for this particular displacement. So we'll be checking the capacity of structure now for the last pushover point. To check the results for pushover, let's check the sequential hinge formation first. Hinge status results under load case X. I'll check the status of yielding under FEMA hinge. I'll check the rotational hinges, because those are the hinges that have been defined for the beams, columns as well as the shear walls. I'll check on legends, deform shape, apply. So as you can see, at the very first step everything is elastic, and as we progress, as we exceed the elastic level, at step 4 you can see some of the hinges are failing in here, and if I observe where these hinges are failing, these are basically in the shear walls. Right, Let me activate only the shear walls. Yeah, as you can see in here, so the very first failure that occurs is in the shear walls. The shear walls located in here are exceeding the D point. Basically, if we since we define the pushover hinge in here, this is the FEMA curve, and if it exceeds D point, that means the residual strength might be left in the member and it has completely failed. So by performing pushover analysis, we can actually see which are the members from where the cracking is initiating or the failure is initiating, and since we have to avoid the performance of the structure entering the failure, so to limit the performance of structure below life safety or below collapse prevention, of course we never design the structures between life safety or collapse prevention. We limit it generally for life safety, but depending on the investor, if investor is ready to invest more amount or for important structures like hospitals or schools, we do go for below immediate occupancy. So depending on whatever performance level that's required from the structure for each and every element, we try to strengthen it so that the failure can be avoided and we can restrict it, bring it down below these performance criteria. So as you can see, at very initial stage, at step 3 it's completely elastic. At step 4, as you can see, the failure in the shear walls, that means we need to do the strengthening in here. If we strengthen this, then that means that we can avoid the sequential failure which is occurring due to the force redistribution due to the failure of the walls in here. So if we strengthen this shear wall, we can prevent the further hinge formations, the sequential hinge formations which are occurring in the upper stages. Likewise, we can check for y direction. For y direction, as we can see, this particular shear wall is experiencing the hinge formation in the first stage, and then you can see sequential hinge formation in the beams, but beams are below immediate occupancy, so should be acceptable. For the maximum level, as we can see in here, some of the members have exceeded the life safety level as well, as it can be seen from here, from the color itself. These are the shear walls which are exceeding the life safety, whereas the beams have exceeded the immediate occupancy and they are between immediate occupancy and life safety. So we can interpret these hinges from the colors, that where they lie and where we need to strengthen the structure. Generally, the shear walls have larger thickness at the base and smaller thickness at the upper location, that can prevent the sequential hinge formation. Right now in this particular tutorial model, I think it's the same thickness. Yeah, only one thickness has been used for all the shear walls. Maybe we need to have larger thickness here so we can restrict the failure over here itself. So that is how it is helpful. We can check it graphically as well as we can check it in tabular format. So let me check the beam summary table. I'll be checking for X and Y. We have to check the rotational hinge, so we'll go to RY, and as you can see in here, it tells you the status of the hinges for different steps. As you can see, for the element number 1, the maximum hinge formation can be checked from here. These are the forces in the member. These are the elastic deformations, plastic deformations, to yielding d over d1 basically. So d1 is over here and the member is elastic. So element number 1 is never entering the plasticity. As you can see, some of the members have exceeded B plus in the sense that they have exceeded B. That means they are behaving non-linearly, but they have not exceeded the immediate occupancy yet. So B plus elastic, this is the situation of the hinges in beams. Some are exceeding the immediate occupancy, that means they are between immediate occupancy and life safety. From the diagram, I didn't observe any beam exceeding life safety, so maximum I think we will get is immediate occupancy plus. So none of the hinges in the beams are exceeding the life safety level, so should be acceptable if unless it's a hospital or some important structure, or unless the investor wants to design it for below immediate occupancy. So beams are all okay. This is not just the beams as well as the columns. So what I mean is the frame members. Let's check for the walls. Walls are the ones having failure. So wall summary. I'll get it basically for the lower stories, because lower stories are experiencing the maximum failure. We have to check the rotational hinges. Since our shear walls are slender, I have used the rotational hinges. For squat shear walls, we do use the shear hinges. Now as we can see, for different shear walls at top and bottom, these are the situation of the hinges in here. The first floor, I've got the rotational hinge in the shear wall, wall ID 1 at I end. Maximum is 20. Elastic deformation, that means it has exceeded the elastic. So I'm getting immediate occupancy plus. As you can see, for the shear walls that I have selected, I'm getting immediate occupancy plus and elastic. Let me check for all. Let me check for all the shear walls. Wall summary. There are 4 wall IDs only. I'll select load case, say just for X direction, load case X. I'll select all the stories and I have defined RY hinge. So I can get in here that at the 10th floor level, whatever shear wall is there, at the 11th floor, at the 12th floor, by floors and with different wall IDs, I can get the sequential hinge formation results. And as you can see, hinges exceeding the life safety levels in here. Some are elastic, some are beyond immediate occupancy, exceeding the life safety as well. So these seriously need to be brought down. Basically these are at the 3rd floor for wall ID 2. So wall ID 2 is this particular shear wall, and at 3rd floor level, that means the failure in here. Anyways, we can check those from these tables. And finally, as a summary of the hinge formation, we use the story hinge status. Say for X direction, we'll get the summarized output for the number of hinges for the entire structure. So for pushover load case in X direction, at the very first step at 1st floor level, all the hinges are elastic. As you can see, none of the hinges are immediate occupancy, life safety or collapse prevention levels. In the initial steps, of course, it's got to be elastic. Let's scroll down and go to the last step. Step number 20 for load case in X. At the roof level, only beams are located, so only beam hinges will be there. Let's check at the 12th floor level, where there will be beams, columns and walls. So beam member here represents the beams and columns hinges. A total of 170 are elastic, 38 have exceeded the B point, they are between B and immediate occupancy, and 20 hinges have exceeded the immediate occupancy, they are between immediate occupancy and life safety. So none of the hinges are ever exceeding life safety. Whereas for the shear walls, there are 8 elastic hinges in here. Alright, so at the upper story no failure, but at this particular level, for example, at the 8th floor level, we can see that 4 hinges are elastic and 4 have completely failed. If you scroll down for the shear walls, the lower stories are the concern. So we can check at the 1st floor. As you can see in here, at the 1st floor in the 19th step of pushover, only 1 hinge is elastic, 2 of them have exceeded immediate occupancy and 5 have completely failed. So that is how we can check the summary of the hinges, and ultimately whatever is the performance level of the structure, we have to bring it down below immediate occupancy or life safety, whichever is the desirable performance level, by local strengthening or the rehabilitation measures. Let me stop the video now.